has authored more than 30 research articles in reputed journals and international conferences. So his research interests include wireless sensor networks, wireless body area network, vehicular ad hoc networks, neural networks, fault diagnosis, machine learning applications, and Internet of Things. So this is all about our speaker. So please, Dr. Rakesh, you can start with your presentation. So please do share your screen and you can do start your presentation, please.
Okay. So may I audible?
Yes, you're very much audible. You can do share your screen with your presentation. Thank you.
So first of all, I'm thankful to Nikhil sir giving the opportunity. I'm also thankful to the organizer and the convener invite us and giving the opportunity. And it gives me always immense pleasure to interact with you.
Thank you. Thanks a lot.
Thank you.
It's our pleasure also. You can do share your screen and present it. Okay. Thank you.
Okay, can the screen is visible?
Yes. You're loud and
Okay.
clear and your screen is also visible.
Okay,
Yes.
thank you. Okay, so let's start the topic here. So my topic here, composite fault diagnosis for the wireless sensor network. So as all of you, I think familiar with the wireless sensor network. So just I'll give the introduction. What is the wireless sensor network? So basically, the wireless sensor network is the collection of the sensor nodes, and they have collected the physical data from the environment and then process it. And whatever the collected data, basically you have to collect it by using the base station, and sometimes what happen, we have to collect it through also the internet or the cloud also for the remote users. So here the whatever the sensor nodes are there, basically the driven by the battery, and these are the resource constraint, are they are very low computational devices are there for the wireless sensor network. We have used here to deploy different way of to deployment is there. So basically the sensor network, if you see the any devices architecture, you can see this is the architecture, very simple architecture is there. Contain the sensor for the sensing unit, and a processing unit are there, contain the processor and some storage are there, and very low computational power is there here, and also storage is also very less. And a transceiver is there, transceiver unit is basically used for the transmitting and receiving the data, and a power unit is attached here. And whatever the data line here is here, these are the optional part is there for the sensor devices. Basically here the location finding system, if you want to know the location of the sensor node, you can add the GPS here, the location finding system. And if you want to a mobile node, you can go for the mobilizer here, and also power generator you can attach. But here very expensive if you add this type of the location finding system or the mobilizer, these are very expensive. So basically we need a low computational power sensor networks. Okay, so they how they communicated, basically this sensor network are communicated wireless communications. Each sensor node having its carrier sense range and also the transmission range. So here in this figure, you have seen the whatever the circle is there, like this is the transmission range of each sensor node. So whenever you have to calculate the Euclidean distance here, if it is within the transmission range, then this will be the node are connected, and the virtual link will be established here. And this is the communication graph. You can say that the node are connected to each other if they are presented within the transmission range of the each other, and they send their data to their neighbor, and basically the multi-hop person they have sent their data. So again, it is depend upon the application how they send their data. Either it is multi-hop or either it is single hop. So basically for the surveillance system and monitoring system, whenever you have to deploy more number of sensor network, and it go through the multi-hop communications. But if you see in the healthcare system, and basically we need whatever the data is there, very precise data, very precise are there, and the data are very what effective data are there. So that's why I go for the single hop communications. So here the OLST they are connected to each other and send their data. and the data we have to connect it either base station or data connected to the remote user through the cloud or the internet. So as there is a various application of the sensor network, you already know that sensor network used for the monitoring, surveillance, sensor network used for the military, environmental monitoring, you can use industrial purposes, smart buildings, smart grid, healthcare system. So very large scale of application is there for the sensor network. So here one thing is there for the whenever you have to deploy the sensor network, large number of sensor network in a human inaccessible area and the harassed environment. Okay, it is very difficult to maintain the sensor network. Okay, sometimes what happen, it is very difficult to replace the sensor network. Also, replace the battery. It is very difficult because it will be human inaccessible sometimes. Suppose you can say that for the forest fire monitoring or any hill, you can deploy the sensor networks. So here it is very difficult for the human. Each time it will be go and replace the sensor network, and maintenance is very difficult. So that's why due to the large scale application and large number of sensor network whenever you have to deploy, so here what happened, due to either some external causes or internal causes. Example, suppose external causes, you can say that suppose you have to deploy in a forest for the fire monitoring. Let's say from lightning it happened, earthquake it happened, let's say, or any animal attack. So these are the external causes. The sensor network is damaged for the external. Similarly, for the internal causes like this sensor network for any module, we can say that their transceiver unit will be fail or the any malfunction is occur, any error is occur between the module. So due to the internal causes also, the sensor network behave unexpectedly. So that unexpected behavior of the sensor network we have called as the fault. Okay, so let's see. I'll introduce here the term of the fault, error, and failure, and what is the relationship here. So here I've already told that due to the large scale application, whenever you have to deploy the sensor network in a human inaccessible environment or harassed environment, so what happened, due to the external and internal causes, sensor network behave unexpected. So that unexpected behavior of the sensor network we have called as the fault. So whenever any sensor network is damaged or fault occur in the sensor network, it will be leads to the error. So what is the error? Error is basically here the deviation between whatever the actual result and what is the expected result. What you have to want, but whatever it will be give. So that is the deviation. So due to the fault, it will leads to the error in the sensor network. That is the erroneous result it will be produced. And after that, that error again it will be leads to the failure of the sensor network. Actually, this is the failure sensor network. You can call that it will be unable to perform its regular operations or its routine tasks. Whatever the work is there, routine tasks is there, it will be unable to perform. So that will be leads to the failure. Again, if one part of the network will be failure, then it will be again leads to the fault another part of the network. So that is the relation between the fault, error, and failure between the sensor network. First fault is occurred due to the unexpected behavior, then it will be leads to the error, and again the error will be leads to the failure, and if failure is occur in one part of the network, again it will be leads to the fault in the another part of the network. So that will be maintained. So here what happened? So if a network is failure, so actually that network we have to use some sometimes if say that the critical application also from the human health system, from the safety criticality applications, from the military system. So if the network is failure, so what happened, the data, the decision making process will be affected. So that's why it is necessary to detect that failure or that fault of the sensor network. That's why I go for any prevention technique, that's why I go for any recover techniques for the sensor networks. So here I'll introduce some terminology of this fault diagnosis. So whenever any fault is occur, so first we go for the fault detection. So what is the fault detection here? The fault detection is nothing but you have to detect the presence of the fault in the network. If a fault is occur, so here we can detect the presence of the fault. That is the fault detection. Then after the fault detection, we have both the fault identification. So what is this fault identification? So after the detection, you have to identify the particular node, whatever the location is there. Okay, suppose it is the 2D plane is there, whatever the XY coordinate is there, what is the location is there. So you have to identify that location or identify that node. or you can say that faulty node or fault-free node. You can identify. So that is the fault identification here. Then after that, you have to go for the fault classification. So you have to detect the presence of the fault, then you can identify that particular node, then you have to classify. Actually, different type of the fault are there. Later in this slide also, I'll be explain what are the fault are there. But here, what happens, you have to classify the fault, because for the different fault, different prevention techniques, different recovery techniques are there. So here you have to classify the type of the fault here. What are the type of the fault? So for the classification technique. Then after that, you have to go the fault diagnosis. So here the fault diagnosis is nothing but the combination of the all. That is the detection, identification, and classification. We have to detect the presence of the fault. We can identify the fault, and we can classify the fault. So that is nothing but you can diagnosis of the fault. So you can diagnosis of the fault. So after the diagnosis, we have go to the prevention. That is the either isolation or the tolerance technique. So what is the isolation? Here the isolation is nothing but for the particular node, let's say 100 number of nodes are there, and in the 100 of number of the nodes, 10 nodes are faulty. So here you can isolate that faulty node in our network, and the fault-free node remain as is. So that is nothing but your fault isolation. Then another is their fault tolerance. So here what happen, it is depend upon the deployment. Sometimes what happen, we need the sparse deployment, and sometimes we need the dense deployment. Like more number of sensor node network can need for the dense deployment. So here in the sparse deployment, if you apply the fault isolation technique, so what happen, there is a connectivity issue are there. So that's why I go for the fault tolerance technique. So what is the fault tolerance technique? So here what happen, you have to tolerate that fault. That means you have used that node as a connectivity at the intermediate node. You cannot isolate that node. That means the node, whatever the sensor network is there, it will be perform its routine tasks with presence of the faulty node. That is the fault tolerance. You can tolerate that number of the fault. Okay, so we can, using the fault tolerance technique, we can use the fault tolerance mechanism. So that are the terminology. You can go for that: fault detection, identification, classification, diagnosis, isolation, and then the fault tolerance. Then as we go the here, the classification of the fault. Basically for the sensor network here, the taxonomy here I have given the classification of the sensor fault, basically for the wireless sensor network, whatever the there. So in generalize, the classification is depend upon in the three way. One is the behavior, another is the persistence, and another is the underlying causes, that the special causes. So in generalize, according to the behavior, the fault are classified as the hard and soft. Okay, I'll be explain what are the hard and soft. Here, as per the behavior, it will be classified as hard and soft. So what is the hard? So here hard fault is what? The sensor network which does not respond to its environment. That is the hard fault. Whenever you have to send the data, it will be not respond to the environment. That is nothing but your hard fault. Then as per the behavior, that is the soft fault. What is the soft fault? Soft fault is nothing but what? It will be respond to the network. But here, each time it will be give the erroneous response. That is nothing but your soft fault. Whatever the response is, each time it will be erroneous. That is nothing but your soft fault. Then after the behavior, you go for the persistence. That is the persistence of the fault. So for the persistence, here it is the four category, that is the permanent, intermediate, transient, and bigental. So what is the permanent? Here what happen, whatever the fault is occur here, it will be persist. Okay, the whole lifespan of the sensor node. That is the permanent, whole lifespan of the sensor node. Then what is the intermittent here? It will be follow a pattern. Means at some time period, it will be give the faulty. Then after some time period, it will be fault free. Again, some time period, it will be faulty and fault free. Like a pattern will be maintained here for the intermediate. And then go to the transient. Here what happen? This intermediate, transient, and the bigental, these are the dynamic fault nature. The permanent is the static. The nature will be fixed. For this intermediate and transient are the dynamic type fault. So here the transient here is what? This is very fault is very occur in very tiny amount of time. Means example, let's see in the forest what happened. A lightning is happen. So at that moment, the whatever the sensor node will be produce the erroneous result. After that, it will be again faulty. Okay, then very small amount of time it will be keep the faulty, and in other time it will be fault free. And this thing will be maybe occur or may not be occur in the lifespan of the sensor node. So that is very tiny fault. Okay, the spike amount of time it will be exist. That is for the transient fault, and it is very also challenging task to detect that type of the dynamic fault. And here the Byzantine means it will be mixed type of the fault, means that a sensor node it will be behave like sometime permanent, sometime intermediate, sometime transient. Okay, or it will be maintained. It will be like a mix. Byzantine will be all. It will be a superset of all the fault. So like it will be sometime permanent, sometime intermediate, and sometime it will be transient. So basically, this is the general category fault, that is the behavior, and this is the persistence. As per the behavior and the persistence. Then this is one the special causes, some underlining or special causes. This fault are divided into fail and stop, crash, omission, timing, incorrect, and the Byzantine agent. So Byzantine is nothing but a collection of all type of the fault. But here the what is the fail stop fault? In the fail stop fault is what happened here, the sensor node what they have communicate, but each time it will be give the erroneous result. The communication is done, but each time it will be erroneous result. But here what is the crash fault? Crash fault what happened, the totally system will be damaged. It is one type of the hard fault also. Totally system is damaged in case of the computation, and in case of the communication point of view, this node is faulty in nature. That is the crash fault. Similarly, this type of the omission fault what happened, due to the some traffic congestion, energy depletion, due to this the omission fault is occur. Here what happened, sometimes sensor node what happened, unable to perform the task within the deadline. That is the omission fault. And here the timing fault is what, sometimes what happened, it will be sometimes too fast and sometimes too low. The timing, whatever the synchronization is done, it will be a problem. There is a problem or affected, so that sometimes they will be performing tasks too fast, and also sometimes it will be too low. And in the incorrect computation is what it is one type of the sub-permanent fault. Whatever the result it will be given, that is the incorrect result each time. So these are the special causes fault. Okay, so basically here whatever the work I'll be demonstrate here and we explain here, basically these are the type of the generalized fault, like the behavior fault and the persistent fault. This type of the fault I'll be discussing. So let's see, I'll be show you here one timing diagram here, and with respect to that behavior and the persistent fault, how it will be behave. So this is the time equation, that the observation time. If you observe and see for the normal sensor node, whatever the ticking symbol is there, for each time it will be give what the erroneous result. Sorry, this is the fault free behavior. Each time it will be give the fault free behavior for the normal sensor node. But here, whenever you have to go to the hard permanent faulty sensor node, you can see that this is the dotted. That is nothing but the not respond. Okay, each time it will be not respond for that node. For the hard faulty sensor node, each time it will be not respond. But whenever you have to go to the sub permanent fault, here what happened? You can see that this is the cross symbol. Each time it will be respond. But whatever the result is there, it will be what erroneous result. But here the intermediate what happened? It will be maintain a series. Means at some point of time it will be fault free, then faulty, then fault free, faulty. Okay, that pattern will be maintained in intermediate fault like this. And in the transient fault, what happened? Very small amount of time it is faulty, then it is fault free like this. It will be maybe happen in the other time also, but very small amount of time. If you compare it with the time diagram of that fault, that is the classification. Then these are the some performance matrix are there for the fault diagnosis performance. We go for the fault detection accuracy, false alarm rate, false positive rate, the false classification rate, detection latency, energy consumption, and the fault drop. These are the performance matrices basically for the, if you go for the fault diagnosis, and these are the performance matrices. Okay, I'll not discuss more than here. Just I'll tell you whatever the detection accuracy, what it will be just a ratio, whatever the fault will be detected, and whatever the total number of fault will be present in the network. Similarly, for the false alarm rate, whatever the fault-free node is detected as faulty and divided by total number of fault-free node is present in the network, and whatever the false positive rate is nothing but whatever the faulty node detected as fault-free to the total number of faulty node present in the network. And this is the false classification rate, that is the negative classification cost of the false classification. Similarly, detection latency, you can calculate how much time, whatever latency you have to need it here for the fault detection, and how much energy will be consumed, and how much fault probability you have to give it for the faulty. So these are the some diagnosis performance matrices for the fault diagnosis. So these are the challenges here to design a fault diagnosis technique. As you know that resource constraint, or as it is a wireless sensor network, it is a less power and less storage devices and energy constraints. So these are the resource constraint problem is there. And random deployment, that is problem, because you can deploy the sensor network, and here the dynamic network topology is there. Sometimes we can add more number of sensor networks, so the topology will be changes. Sometimes you can remove the sensor network, so the topology will be changes, and it will be needed scalable, reliable, and robust. So here what happened, the node will be here scalable. Okay, sometimes you can add more number of 30 nodes. Sometimes the node density will be added. So here this is also challenges. And then highly accurate and low cost, and the connectivity and link quality also a challenges tax. How they connected and link quality is also important. And again, the false isolation and fault tolerance, this is also after the fault, which methodology can follow the fault prevention, that is also these are challenges are there. And basically these are my motivation here for that. Here whatever the work I'll be discuss, whatever the solution I'll be discuss here for that fault diagnosis, these are the motivation here. One is the application of the neural networks. Okay, because as you know that whenever for more number of sensor node, you have to deploy whatever the historical data you have to find, whatever the exemplary data you have to find, you have to go for that neural network to design the network, and then find out the faulty node. That is the application you can use here. Then the sparse network, dense network, whatever the diagnosis algorithm you have to design, it will be work for both the sparse and also dense network, because different deployment are possible, sparse and dense are possible. And again, it is node failure and link failure. This is also important here. If it is a node or link failure, how you can distinguish between that node failure and link failure. Then this is the important, the composite fault environment. Okay, that is what happened. And whatever the previous algorithm are there, researchers algorithm are there, they have basically concentrated in the single type of the fault. But now the state of art is what we can go for the heterogeneous type of the fault. That is the composite fault. Different type of the fault, you have to the combination the type of the fault. That is nothing but a composite fault. You can take the soft fault, hard fault, permanent, intermediate, transient, all type of the fault. That means a single solution you can give in, so that it will be deal with composite fault environment. It will be detect, diagnose all type of the fault. So that is the important. That is the composite fault environment here. And whatever the algorithm you have to design here, it will be a lightweight and low cost. Okay, due to the resource constraint, you can go for the lightweight and low cost. And here also simultaneously you have to detect some faults and ports also. Due to the faults, some portion of the network but disconnected to the total sensor network, so you can go for the ports also. And whatever the design is there, that is the robust design of the fault tolerant sensor network. So that are the motivation here. Okay, let's try and discuss one solution here. So here the composite fault diagnosis, I already told that what is the composite. It will be take a heterogeneous type of the fault, different type of the fault to diagnosis. So here a fault diagnosis protocol, that is the composite fault diagnosis protocol, is proposed from using the statistical and a neural network approach. Basically, the protocol is used analysis of variance, the ANOVA method for the fault detection, and here with the significance level, and the PNN, that is the probabilistic neural network used for the fault classification. This is one solution I'll be keep, and a different type of the solution are there. Here I'll be keep using here. Here the performance is analyzed here. Whatever the protocol is there, it will be analyzed by the simulation, and also the validation is done by the experimental test bed also. Okay, for the real life applications. So let's take the assumption. As you know that for the fault, any sense, any protocol you have to design, you take some assumption here. So here our assumption is here sensor nodes are static in nature. Here whatever this particular solution is there, this is probably for the static network. It is not but for the mobile network. This is a static network, so that we can take the sensor node as the static in nature. And sensor node are the homogeneous nature. Sensor node are the unique identification. And here the coordinator node. Actually, here I am using a coordinator node. Basically, for the computation, the coordinator node will be compute the faulty node, and that coordinator node is the fault-free nodes. Later, I'll discuss that thing, coordinator node. And the virtual links are fault-free. Okay, so for this particular problem, I will not consider the links, so that the link here are the fault-free. That are the assumption for that particular problem. So let's take the network model. Very simple network model. Whatever the number of sensor node are there, it will be deployed. Whatever the region is there, it will be deployed. And here the link will be established. How the link will be established? If the distance is less than equal to the transmission range, then the link will be established. Otherwise, the link will be not established. That is the network model, and it's the simple network model. Actually, what happened here? The sensor nodes are there, and here you have to calculate. Suppose the power, that is the receiving power. Using that receiving power, that is called your RSSI, the receiving strength signal indicator. Using that receiving RSSI value, we can design here the some anchor node, and that anchor node with that member of the node, that is the cluster, will be formed using that receiving power. Okay, that what happened here? The cluster node, or you can say that here the coordinator node compute the fault diagnosis algorithm. Very simple model are there here for the network model. Then the fault model, that the fault we have taken here, I have taken here the hard permanent, soft permanent, intermediate, and transient. I have already discussed what is the hard. It will be not respond to the network, and soft permanent, you can say that it will be respond with erroneous data, and intermediate, whatever the arbitrary result, it will be give to the surrounding, and transient is what very instant out of time, it will be give the result as the fault. So that is my fault model. So that is my communication model. Here the communication is important, as you know that whenever you have to send the data, the communication is very important here, because the MAC layer is directly attached to the radio of the sensor network. That we can say that we can adjust the energy here. Energy consumption is dependent upon that MAC layer. So here the communication model, whatever the communication model, again the fault detection also, the communication model is important, because whatever the packet, if more number of packet is dropped, so sometimes what happens, the drop packet is treated as the faulty node. So that's why communication also important. So here I am using one multi-channel MAC protocol for the communication. So here is my synchronization frame, some frame are there, and these are the, actually this is the combination of your CSM and PDM based approach, the carrier sense and the time division based approach. Here one control page are there, and the data pages are there. In the control page, what happened, they are fixed their communication, and after that in the data page, they have performed their data, they are communicate their data. So these are the main thing here, and that will be explained here. The control page and data page, what happened, these are the slotted control page. In the control page, what happened, the particular source and destination are what, their handshaking is done. Then whenever the handshaking is done, then what happens, they have to select a data channel for the data communications. So they have shifted the particular data channel, or after that, whenever they will be shifted the particular data channel, other sensor node are the split. Only that sensor node will be perform their communication, and it will maintain a multi-channel. So what happen, the packet delivery ratio will be more here, and the latency, you can say that delay will be very less, and you can also adjust the energy consumption. So that is actually I'll be design here the hybrid, actually with CSMA and with the TDMA hybrid approach is there in our medium access control protocol for the data communication part. That is for the communication model. And then for the energy consumption model, actually I have used here the network simulator NS2, and the NS2, it will be give the three type of the consumption model. One is your free space, another is shadowing model, another is two-ray ground. So what happened, I'll be use the free space model for the general simulation purposes, but whenever I'll be go for the test bed, and after the validation of the test bed, I'll be go for the shadowing model. The model is already available in our simulation. So some formula is there for calculating the receiving power and also the transmitting power. But here what happened, the transmitting power will be more here. In our case of the sensor network, whenever it will be transmit the data, that time energy consumption will be more. That is clustering phase. Okay, why clustering phase? See, fault diagnosis also different type of the algorithm is there. Either it is a centralized, either it is a distributed, or it is semi-distributed. So here actually it is a semi-distributed. That means each cluster head, or you can say that here my coordinator node, it will be computes the fault diagnosis algorithm, and that is whatever the inter-cluster communication is done here. So basically, how it will be compute here? So initially, the sensor node are deployed randomly. After that, some tested node, some coordinator node here is deployed. Then after what happened? That coordinator node send a signal to the sensor node. Then after what happened? To getting the signal, they find out the RSSI, whatever the receiver strength signal. Then using the distance, and they have first cluster. With that cluster, whatever the coordinator node are there, they form the cluster. After that, a load balancing cluster mechanism are used here to reduce the energy consumption. A load balancing cluster method is used to reduce the clustering energy. But here basically the whatever the coordinator node are there, the cluster head is compute for that particular problem. So let's see first type of the fault, how to detect it here. That is the hard fault. Okay, hard fault detection. So basically I already told that basically the hard fault is what? It will be not respond to the network. So here for that hard fault, for each sensor network, it will be maintain a register here, and it having three values. One is 0, one is 1, another is 2. 0 is it is the fault free, 1 is it is a likely faulty, and second is the then it will be confirmed as the fault. It is a faulty. It is a permanently faulty. So for each faulty, here I have maintained a window. This is the time out window. So in that window, what happened? It will be slotted, and it will be contain a timeout period. So what is the timeout period? Basically, it will be your RTT, round trip time, and it will be what? It will be the summation. We can say that the propagation time, transmission time, processing time, and the queuing time. Whatever the time are there, that is the round trip time. So each timeout period, whenever the sensor node sends the data to the coordinator node, then what happened? The coordinator node send the messages, then after that sensor node send a acknowledgement. So if it is not received at that time period, what happened? They will be make into the value will be changed. Okay, if it is received, then the value equal to 0, that means it is fault free. Then if it is not received within that timeout period, then the value will be changed. That is will be made into 1. So in this way, it will be contained. A period, the observation period will be done. Suppose I have take 1 to time t, and that will be maintained. After that, what happened? I have taken a summation of that register and taking a threshold value. Suppose the total time equal to here observation time t. And if it is a 50% or greater than 50% time, it is not respond, then it will be changed. The value will be changed to 2. That will be considered as the faulty. That is for the special, the hard faulty. If it is not respond, that the timeout window mechanism is used. Then for the short faulty here, a statistical based mechanism is used, that is the analysis of variance, and it having the two hypotheses. I am not discussing the detail here, just I am telling the two hypotheses here. What is the null hypothesis and the alternative hypothesis? Basically, the null hypothesis is tested if there is no significant difference between the mean of the sensor value of the sensor nodes. And another alternative hypothesis tested what? If at least one significant difference between mean of the sensor node. So actually, whatever the coordinator node is there, it will be perform this testing, that is the null hypothesis and alternative hypothesis. And if the significance level is there, we can set the significance level to test it, so that you can find out what type of the fault are there. So here you can detect. Okay, here you can detect the faulty. Then after the detect of the faulty, we can go for the classification. How to classify? As you know, the different type of the fault are there, like permanent, intermediate, transient fault are there. So for different type of the fault, you can need the different prevention technique or recovery technique. So that's why you go for the classification also. We can classify what type of the fault are there after the detection. For this particular problem, okay, I'll be use that PNN, that is the probabilistic neural network approach. So why I am using this PNN? Basically, the PNN is what? It's just a classifier. It will be map the input pattern to corresponding output classification, and whatever the magnitude is there, it will be very faster than other neural network like the gradient descent approach for the PNN. And if PNN having no local minimum problem, and it will be having a optimal classifier, you can say that. But PNN method is dynamically processed because the training sample you can add it and remove at any time. Okay, so that's why it will be use a PNN, and it's also very low cost here. No so much training you have to require, no weight is required here like this PNN. So this is the structure I can here I am shown here. This is the architecture of the PNN. You can see that this is the four layer are there. One is the input layer and the pattern layer, and this is the summation layer. This is the output layer. So basically here the probabilistic neural network is what happened. Uh, Whatever the input you have to give in, okay. So here some exemplary or the feature vector is maintained in the pattern layer. So you have to calculate the distance between the particular input and the pattern layer. That is the Gaussian distance formula is used here to find out the distance. After that distance, you have to calculate the average PDF. That is the probability density function here. And here, whatever the value is there in the summation layer, which value is the greater, for the probability value is greater, we can find out the particular unknown input is the belongs to the particular class, whatever the different classes are maintained here. Like this example, let's see, I have taken the input here, some sensor data is there. Suppose here 3 type of the fault are there, means 3 type of the class are there. 3 type of the class are there. Then here the Gaussian distance is calculated here, and here it will be find out the probability density function summation. After whatever the for each input you have to calculate whatever the feature vector are there. This is the number of type of the fault. So whatever the distance here you have to see which is the maximum, it will belongs to that type, because that is the probability neural network here. If the distance will be more here, so that it will be close to that class. If distance will be less, then you can say that it will be far from that class. So that will be maintained here. And from that particular symbol, you can say here, if you find the 3 value, the 0.2, that is the maximum. So that particular input is belongs to that type of the class 3. So that is the different type of the fault. It depends upon the pattern layer, is depend upon basically the type of the fault here. So here that is the architecture. You can say the actual input and output, the PNN is used here. Okay, I'm going to discuss here. Then go to the implementation part here. I'm already told that I have used here two simulation and also the test bed. So let's see for the simulation. I have used the network simulator, that is NS 2.34. And here whatever the parameter I have set, the number of sensor node, deployment area, carrier sense range, and the whatever the duration of the frame. Actually whatever the MAC layer frame I have designed, what is the duration of the frame, the control period, the control phase slot, data slot, like this. And power also, whatever the receiving transmission power, and whatever the channel rate, whatever the model you have to use. So that is my simulation parameters basically for the network simulator here I am using. Then after that, this is my some results here. That is the first result, that is the composite faulty node detection accuracy with respect to the fault probability. So here what happened, the fault probability will be increased. We can add more number of fault, and 5%, 10%, 15% like this. And so how it will be work with respect to other algorithm, other existing algorithm. Here it will be so, that is the fault detection algorithm. Next is the parameter is the false alarm rate with respect to some other algorithm. So that is the false alarm rate. We can say that how much faulty node is wrongly detected as faulty. So what is the with the proposed algorithm, with other algorithm, that is the result of the false alarm rate. Similarly, this is the false positive rate. That is the how much the faulty node detected as the fault free. Yeah, wrongly. So that is the fault positive rate with other algorithm, and this is the proposed algorithm, and this is the false classification rate. And you can see this is the one bar is there. Why? Because whatever the other algorithm is that they have not detected the heterogeneous faults. That's why it will be give the single fault classification rate of the proposed algorithm. And then go to the test bed experiment. Whatever the test bed experiment I have taken, basically this is the sensor node I have taken, DST1 temperature and humidity sensor. The transceiver I have taken the MRF24J40MA, and the transceiver having the transmission capacity having 120 meter in the indoor environment and in the 200 meter in the outdoor environment for the particular the transceiver unit, and it is the standard of IEEE 802.11. 2.14. That is the transmitting power will be that, and this is the standard IEEE 802.15.4, and is the operating frequency, selected frequency, that are the receiver sensitive, packet receiving threshold, number of sensor node having 10 sensor node are there. So like this, these are the experimental parameters. So here I've shown that the sensor node here, what the sensor it will be contain, that sensor DST1 temperature sensor it will be contain, and this is the transceiver unit, that is the MRF unit, IEEE 8015.4 standard, and it having the 120 meter in the indoor environment and 180 meter or 200 meter in the outer environment. That is the transceiver unit at the capacity. And this is the microcontroller I have used here for the basically the Arduino board I am using, and the for programming embedded C is used. But this Arduino board is fixed here, and this is the battery. Actually, a rechargeable battery is used here. So this is the simple device. Okay, this is the simple sensor module. Like this sensor module, we have designed 10 number of sensor module, and this is just a overview of the sensor module in the indoor environment. Okay, that's lab. This is the 10 number of sensor node is deployed, and this is the outer environment, and 10 number of sensor node is deployed in the outer environment. The same, whatever the sensor node are there, this is the replicate here, duplicate sensor node created, and this is the deployment is there. Then what happened? You have designed also a coordinator base station to collect the sensor node. After that, that coordinator node is connected to our base station for the computation. So here, this is the indoor environment. The base station is there. It will be collect all the sensor data, and the computation is done here. And basically, for that computation, I use the MATLAB for that test bed. Whatever the data is collected, after whenever the program is run in the base station, I'm using the MATLAB. And this is the outer environment, and the outer environment, this is the base station. Whatever the data is collected to the base station, and this will be run here. So that is the collection. You can say that the coordinator node, and it will be connected with the base station here. So these are the experimental results of the fault detection accuracy, whatever the number of faulty nodes are there. Similarly, the false alarm rate, number of faulty nodes are there, and false positive rate, and this is the false classification rate for the experimental purposes. Okay, so this is one. Then I'll add another thing here, that is the fault. Okay, so I already told that what is the fault node are there. So then I'll be introduce one term is the CORDS. So what is CORDS? Let's see what is the CORD. So you can hear two types of there. One is the CORD node, another CORD link is there. So what is the CORD? So let a network, if you say that the network is a graph having the vertices and edges, be a connected graph, and if there exists any node, okay, if you remove that node or the disconnected of that node, okay, component of the node, and that node will be disconnected the total graph into two or more components. That is nothing but your CORD node. Similarly, for the CORD link also, for that disconnected of the that link, you have to find the more number of components in the graph. So you can introduce here CORD node and CORD link here. So here the two claim here I am introduced. If the connected network, whenever there exists a CORD link, there also exists a CORD node. Similarly, if a connected network, if there exists a CORD node, then there may or may not exist a CORD link. So this is the scenario here. You can see the example. Suppose this very simple network is there. Suppose for that network, this red color node is the faulty node. That means it is not a response. So whenever you can see that if it is due to this node, particular node N2, the total network is divided into two parts. So we can call as this is the CORD node also. So here N3 also, this is also one CORD node, because if you disconnected that node, so that the total network here divided in four parts. This is one part, this is one part, this is one part, this is one part, this is four part. So these are also CORD node. And you can say that this is the CORD link also. So here what happened, if you disconnected that link, it will be divided the total network in the two parts. Okay, so that thing also we are need to detect it, what is the CORD node is there. Basically here see what is the problem here is what whenever the source node sends their data to the other nodes here, the destination, and let's see after some time these two nodes are the faulty. So due to the faulty, what happened, the messages here will be not reached. Okay, because this is the faulty node. So these two nodes is divided this total network into two parts. Okay, that is, you can say that is the CORD node. You can say that these two nodes are the CORD. It will be divided the two network into two parts. So you can say that this is the safe zone, and here it is the CORD zone. So here what happened, our node is detected. Okay, a node is detected, either it is present in the safe zone or it is CORD zone. It will be detected itself that it will be present in the safe zone or CORD zone. So here I'll be using a graph theoretical approach here to detecting the what a node is present either safe zone or CORD zone. Okay, so safe zone, CORD zone, here a formula is used. Actually, potential factor is introduced to find out the degree of the sensor node, and after that some threshold value is used here to find out either it is present in the safe zone or COT occurs from here or it is COT zone. To find out, we can use here. So each node having a potential factor to find out that if the node is present in the safe zone or it is a COT zone. So this is just a simulation here. Here some node will be deployed. So black color node having the COT nodes are there. So this part is in your COT zone. Okay, so particular node here are the COT zone and these are the safe zone. And here these are the simulation here, the faulty sensor node detection, false alarm rate, and this is the whatever the normal node, whatever the potential factor is there. But for the COT node, what happened? After some point of time, you have to find the potential factor will be degrades and it will be 0. Each node will be find its own zone. What is if it is present in the COT zone or it is a safe zone. And similarly, I already told that after the fault detection, you have go for the either fault isolation or fault tolerance. But problem is that fault isolation, if you isolate the faulty node into the network, so what happened? The connectivity issue will be occur. Okay, the node connectivity issue will be occur. So that's why I go for the fault tolerance mechanism. So here I'll be use some regressional technique, simple linear regression and also some stepwise regression also, and find out a relationship between the neighbor nodes and whatever the particular node. So here what happened? The particular node is there, and this is the neighbor node. Then a target sensor node, and this is the predictor sensor node. So using that neighbor sensor node, you have to predict the value. Okay, if you predicted the sensor value. So here the different type of the neighbor sensor node, degree of the node are there. Suppose 3, 5. Okay, increasing the number of the sensor node, and you can find the prediction. Whatever the real value is there, then whatever the predicted value are there. So these are the whenever you have to increase the number of neighbors, so the prediction will be more accurate. That is the fault tolerance. Means you can tolerate that fault. The presence of the fault also, the whatever the routine tax is there, the regular tax is there, it will be going on. No problem which occurs. Okay, so basically this is the occurrence. Then this is my final conclusion. Here some fault diagnosis protocol has been proposed using some timeout mechanism, neural network, statistical approach, and the neighboring coordination approach. And that proposed protocol are used to find out the composite fault environment, basically the hard, soft, intermediate, and transient fault. And here both simulation and the test-based experiment is done for the validation purposes, and different type of the matrices is used like fault detection, false alarm rate, false positive rate, used to find out what the performance. And whatever the experimental implementation is done, that will be so what that is the feasible implementation in the real life applications. That is my conclusion. And in the future plan, you can say that you can go for the mobile network, whatever the dynamic mobile network is there, how to find out the faulty node in the mobile network, and you have to extend the application towards the IoT also, so that it will be smart computing, it will be highly accurate services will be achieved, and you can implement, you can differentiate also the faulty node. Sometimes whatever the malicious node are there, you can also differentiate that type of the node. And here whatever the research work we have discussed here, we can explore in the body sensor network. That is one emerging field of the application towards the human sustainable life also. And here whatever the hardware driven program, it will be integrate whatever the IoT and ML, whatever the thing we can integrate, so that you can find more number of efficiency algorithm and highly accurate algorithm. So I'll be show one here the future plan. Let's see it for the mobile network. So here what is the difficulty is the find out the collection of the network. So you can go for the good traversing algorithm, how to collect their data from the sensor network, so that you can go for the fault diagnosis algorithm. That is one challenging task here. From the traversing algorithm can go for the fault diagnosis here. Next is for the recent topic, that is UAV emergency communication network. Whatever the connection is there from the sensor network, here you can find out the faulty. You can introduce that the faulty also, this communication network. That is also one future plan here. So that is my some of my work which related to the fault diagnosis, some of the journal works which will be related to my fault diagnosis from the wireless sensor networks. Okay, so let's if you have any question, you can ask. Thank you.
Yes, so any questions from the participant side?
Sir, I have a question, sir.
Yes. Yes.
Sir, have we, when we design a fault tolerant system, we
Yes.
for sensor network should evaluate with respect to energy.
Yes. Yes.
So energy conservation for that, we can use machine learning
Yes.
based techniques like neural network. They have an overhead, sir,
Yes.
because
Yes.
I think
Yes,
so.
ma'am. Actually, what happened, whatever the machine learning technique basically used for the classification purposes here. So what happened, whatever the classification is done, basically we have taken the historical data, and for the historical data, the training will be done. Okay, so once the training will be done, actually from the historical data, the training side will be done. So at that time, what happened, the training will be complete. After that, for the testing purposes, only you can go for that. I mean, whatever the sensor data is there, you can send the data, you can classify it data. And whatever the classification is done here, see, I am using here one of the probabilistic neural network, PNN. So here, what happened? Here there is very less consumption here. No so much training is required here. No weight is there. That's just exemplary vector you have to set, and that exemplary vector you have to calculate the Gaussian distance and find out whatever the classification. So basically the training side you have to done using the historical data, so that you can say that we can reduce the energy consumption here.
So
Okay.
thank you, sir.
Yeah, good afternoon, sir.
Yes, sir.
Sir, actually, my
uh,
question is, suppose I'm getting one data set.
yes, yes.
Okay. So from that data set, how can I determine that this belongs to intermittent fault or the transient fault?
Yes, okay. So basically, whatever the see, I'm using here the algorithm. I can say that is a statistical approach here, uh, like this. That is the I'm using here suppose analysis of variance method. So here actually a significance label is set. Basically, what happens the permanent data for the whole lifespan, whatever the lifespan is there, it will be give the erroneous data. But the intermediate and transient, what happens the intermediate will be regular time interval and transient very spike time interval. So here a significance label will be set, and that significance label you have to set in this way so that it will be cover all type of the faults. It will be just detect at that case. Suppose I'll be set, suppose the significance label it suppose 0.05 to 0.9, so that it will be detects that all type of the fault, intermediate transient, it will be collect. After the detection, then you can go for the classification. So here you have to classify here the type of the fault. Well, it is a permanent, it is a transient, and it is a intermediate. So basically, it is the significance label. If you go for the statistical test, then the significance label you have to set so that it will be detected your type. Because the transient, you can say that it will be the intermediate fault or transient fault. It is a dynamic fault. For the transient, it is very spike fault, so that we can reduce the significance label. We can find out what type of the fault it is for the detection.
Okay, thank you, sir.
Yes, sir. Thank you.
Okay, I think so. This is it, I guess. I am not getting any sort of questions from other participants. Okay, so thank you, sir.
Yes,
It is a very nice presentation.
yes,
So on behalf of CSE Department ITR, I'm grateful to you for sharing this grateful thoughts about this composite fault diagnosis for wireless sensor network. And from the today's talk, we have learned how to build an automate fault diagnosis technique in sensor network environment monitoring system. And also you have exposed a lot of the future plans for the research also. and, and again, I'm thanking all who is helping me directly and indirectly to make this webinar successful. And again, I am thanking all the participants who have attended this webinar. So thank you all also. So who is making a great success to this webinar. Thank you, sir. So I think we can conclude the meeting here. Uh,
So some
are we-
students are still joining. Yes, sir, we can. Thank you,
yes,
sir.
yes.
Rakesh, sir, thank you so much for
thank
giving
you,
your.
Thank,
ma'am. Thank you, sir. Thank you,
thank,
thank you. Okay,
thank you
thank
all. So okay, okay.
thank you.
Thank